In this lesson, we're going to go over the variable declarations in C++. Variables you have to declare ahead of time before you use them. What do we mean by variables? Again, variables are modifiable memory locations. They're going to be names. You're going to see them as names that will hold information that can change throughout the program, as opposed to constants or constant variables, which cannot change their values. In any case, there are different kinds of variables that you can declare, different numerical types. So why is that important? Well, you want to only use the variable type with the amount of memory allocated to it that is most efficient for the job. In other words, you wouldn't want to declare a type that has 12 bytes if all you need to hold is small numbers. Okay, you have to have some idea, perhaps I should do this now, some idea of how variables are stored. So let me do this right here. The most basic memory storage in the computer is a bit. A bit can hold one piece of information that's either going to be 1 or 0. And bits are usually arrayed into bytes of 8 bits. So this can be a 1 or it can be a 0. This can be a 1 or it can be a 0. This can be a 1 or it can be a 0, etc., etc. So if you have two possibilities here, 2 here, etc., two possibilities, then you have 2 times 2 8 times, or 2 to the 8th possible settings for this byte, this register, which is 256. So 256 different states that this memory register can be in. And usually we think in terms of memories being measured in bytes. Okay, and some numbers to remember as we go through this is 2 to the 10th is approximately 1,000. 2 to the 20th is approximately 1,000,000. And 2 to the 30th is approximately 1,000,000,000. Pretty big numbers. Okay, keep those in mind as we go through this. What are variables used for? Inputting values, outputting values, storing and modifying values that you're going to use in the program. There are rules, syntax rules, that C++ demands. First of all, that before you use them, you have to declare variables. The standard is that all variables are declared at the top of the program, inside main at the top. And you want to declare your constants first and then your variables. You'll see this in example code to follow. Variable names can contain only alphanumeric and underscore. I like to use the underscore to separate words. If I have a variable name that contains 2 words, rather than run it all together, I like to put an underscore between words, or to use an uppercase to designate the beginning of the next word. Again, I'll show you examples of this. A lot of system variables begin with underscores, so it's a good idea not to begin with underscore, even though that's legal. And variable names must not begin with a numeric character. They can begin with alpha and underscore, but not numeric. So here's some examples. Legal variable names: X, Y, XYZ, underscore hello, Bob, Joe, 12. All these are legal names. Not very good, but they're legal. Illegal: 12 Joe. Why is that? Well, it can't begin with a numeric. That's illegal. Hi there. Can't do that because it has this hyphen in it. Go. That's illegal. So those are 3 non-compilable variable names. Then there are good practices. The compiler will not enforce these rules, but declare variables inside and at the top of your main function. Now you can declare variables thousands of lines into a program, and you can only use it after that, but it's not a good idea. It's good to declare variables only at the top of your program. That way, if you need to determine the type of a variable, you can scroll up to the top of the program and you know exactly where to look to find that information. Alright, give good variable names. Don't name variables X unless you're talking about maybe an X coordinate, or XY or XYZ. Those names have no meaning. Make your names meaningful. You want to abbreviate them so that you don't write long names all the time. That becomes cumbersome. So, examples. Age, if you're going to have a variable to record the age of something. Tire pressure, and you can see I've used the uppercase P here to make it clear that it reads as tire pressure instead of tire pressure or something like that. Lateral distortion, I've used the underscore here to separate the two parts of that word. And you can use comments to further clarify the meaning of what that variable is going to be used for. And again, look at the declaration. It's type and name. Okay, the types. Well, there are numeric types and there are non-numeric types. In the numeric types, there are integer types and floating point types. The integer types hold whole numbers, natural numbers, integers. They are stored exactly. Floating point types are not stored exactly. They're going to be rounded off, and you have to keep that in mind when you're using them. Okay, so the first type that we're going to look at is short integer. You can either declare it as short or short integer. So this declaration, this very first declaration, could have been done as short int shoe size. That would be identical. However, if you don't have to write that, then why bother? I've never done it that way, but you can. So once again, example declarations, it's type and then name. Now in this first declaration, notice that it ends with a semicolon. I have not given it an initial value. You can do that, and I've done that in the second example here with the is equal to 5 there. In the first case, the compiler communicates with the operating system, says, hey, operating system, I need the memory allocation of 2 bytes for a short, and I'm going to label it with the name shoe size, and I want that associated with my program. You get that memory location, and you get whatever is in that memory location. So if I was to output the value of this variable, well, who knows what might come out? It might be 6,285 or negative 45,006. You don't know. It's whatever happens to be left in that memory location. But if you want to be sure that it has a meaningful value from the very beginning, then you can initialize it this way. You can do that with any of the variable types. Okay, and the range of values. Well, with 2 bytes, remember that you have 2 bytes. Okay, you have 256 possibilities here, 256 possibilities here. Okay, so you have 2 to the 16th possible values that can be stored. If they were all zeros, you could call that 0. If they were all ones, then that would be 0 to 2 to the 16th minus 1. Minus 1 because you got 0 in there. 2 to the 16th minus 1 is about 65,000. Okay, with some change. Most people want to be able to record or hold negative numbers. So if we split that so that half of them are negative, then the range of values is going to be minus 2 to the 15th to positive 2 to the 15th minus 1, because 0, or approximately negative 32k to positive 32k, meaning 1,000. And this is what I would like you to remember. That when you declare something of type short, then you can declare, or you can remember or memorize values in this interval from approximately negative 32,000 to positive 32,000. So if it's small numbers you're after, short is the guy to use. Okay, next type, integer. The declaration is int, and then whatever the name of the variable is. Again, name, type. And again, here in the second one, I have declared and initialized. So the type is int, not integer, but int. And then I've got num cars on highway, num boats on lake, etc. The thing to remember about integers is that the allocation is non-standard, and it can be different on different systems. And this can be troublesome, because if you use ints, then on one computer platform, it may work just perfectly fine, and you move to another platform and it no longer works. So if I was writing programs that I knew might be used someplace else, not just right here, I would stay away from ints. It's better to use short and the next type, which is long. So on S&T's system, they're 4 bytes. And with 4 bytes, you have 2 to the 8th, 2 to the 8th, 2 to the 8th, and 2 to the 8th, which is what? 2 to the 32nd. If you split between positive and negative, then the values run from negative 2 to the 31st to positive 2 to the 31st minus 1, of course, because of the 0, or approximately negative 2 billion to positive 2 billion. So if you remember that, that's important. So if you wanted to have a variable to hold zip codes, suppose you did this, short zip. Is that a good declaration? No, it isn't, because zip codes can be large, right? Out in California, they start with 9. What's the name of that television show? 90210. Okay? If you were to put a comma in there, which you should not do not put commas in your numbers, that's 90,000, and that's not going to work. So you'd use an int. Next type, long. The type is actually long integer. The declaration, long, okay, say desc length or num keys. The allocation is 4 bytes, and this is standard, and again, the range of values negative 2 billion to positive 2 billion. That's the end of the integer types. Now the floating point types. So the first type is float. Okay, as an example, body temperature 98.6. So you see we can put into memory decimal values. The memory allocation is 4 bytes, and the precision 6 significant figures in decimal. The way this is stored, 4 bytes. This would be the exponent. This would be the mantissa. Now you might be thinking, with 23 bits, one is a sign bit, 23 bits for the mantissa, that's got to be very accurate, very precise. But when you transfer, remember that is in binary. When you change that over to decimal, you really only get 6 significant figures. Okay, if you need more precision than that, there is the type double precision. The declaration is double, and then the name of the variable, and you can initialize. Again, you can put comments to designate units, for example, or what it's used for, whatever. The memory allocation is 8 bytes. You get 15 significant figures decimal with the double. But once again, you should not use that type unless you really need all of that memory. Okay, the long double is non-standard, but it is very precise. On some platforms it's 12 bytes, some it's 16. It's really unlikely that you will ever need to use a long double. Okay, starting with the non-numeric types. The first one is character. Sometimes you'd like to hold a character in memory. So for example, you want to hold on to Y. That might be a response to a question. The type is character, but the declaration is char. So continue response, and again, if you're going to initialize it, you do it the same way, but you have to remember that it's a character and you have to put the symbol, whatever it is, in single quotes. So might be a Y, might be an N, it might be an @ symbol. Okay, that's the character. There are 256 characters in the ASCII character set. Incidentally, you get 1 byte of allocation. So how are these actually stored? If you look at this 1 byte, how is a Y stored? Is part of it here, another part here, and another part there, and the rest of it just garbage? No, that's the nonsense. We have to map the characters to the positive integers. So the value 0 corresponds to what's called the null character. So where does Y fit in? Well, we have to look at the ASCII character set. There it is right there. The lowercase y, its value is 121. If you change that over to binary, then it fits in a register 1 byte as 121. I don't happen to know what that is in binary. I would show you if I did. What you should remember from all of this is that the digits 0 through 9 are from 48 to 57. Think of it in late 40s, early 50s. The uppercase alphas run from 65 to 90. And then after that, you have the lowercase alphas from 97 up to 122. If you remember the relative order of them, you're doing good. Sometimes you need more than just one character. You need a string of characters. So we have a type string. Now here's the big lie. String is a basic primitive C++ type. All these types that I've shown you are what we call primitive C++ types. The int and short and long and double and float and char. You can take string to be one. It's not. We'll tell you the truth in a later lesson, long ways down the line here. But you can think of it as being a basic type. So the declaration type is string, a name, say first name, and if you want to initialize it, you're going to have to use the double quotes to surround whatever it is that you're going to initialize it to. The memory allocation is actually dynamic memory. We're not going to cover that, but it's going to depend on the size of the string that it takes on in value. Then there's boolean. Boolean type is allocated 1 byte, and it can take on one of two values, either false or true. Now these two words, false and true, are what we call reserved words in C++. In other words, you can't name a variable false or true. I couldn't come along and do something like this, short false. Right. That would be illegal. The compiler would say, no, you can't do this. That's a bad name because it's a reserved word. We'll talk about reserved words in the next lesson, as a matter of fact. So maybe I want to memorize in the flow of a program that we're going to quit something, and that can take on one of two values, either true or false. So I'll name the variable quit, it's of type bool, and I'll give it a value of false. And if I ever need to give it a value of true, I assign true to it. Constants. Constants are very, very important. Now this is not a type. To declare a constant is to tell the compiler, I don't want the value of this variable to change. So we're going to use the modifier const in front of the type. There's a space there and a space here. Incidentally, C++ is case sensitive, so naming a variable in uppercase pi and naming a variable in lowercase pi, they're two different variable names. And it's very forgiving of spaces. I could put one space here, I could put 1,000 spaces there, and it wouldn't matter. It would just skip over it. You can't put spaces in between numbers, of course. If I were to put a space there, then it would take it as 3.14, and that would be the end of it, and it would wonder, what the heck is that 159 doing there? So you want to keep that together. Okay, so when you write const float pi is equal to, what you're saying to the compiler is, I want 4 bytes for a float, I want to name it pi, uppercase, and I want it to be a constant. I don't want it to change. And if you try to change it in your program, it will not compile. For instance, here, later on in the program, I write pi is equal to 4. That's not going to compile. The compiler said, no, you told me to make that a constant. It's not going to change. I'm not going to allow you to change it. Notice that you have to initialize constants. You cannot declare a constant without initializing it. Okay, so why do we use constants? It's very, very important. There are several reasons. First and foremost, if a value is likely to change either soon or later, then you want to make that easy. Now try to imagine this. You write a program for the federal government to calculate federal income tax. You have lots of different tax rates in this program. And the program is 6 million lines of code long. You write it, and all throughout this program you've put numbers like 0.023 in there. Okay, you hand it to the federal government, and they say, well, by the way, we want to change this tax rate from 0.023 to 0.024. You would have to search through 6 million lines of code to find every instance of 0.023 and change it to 0.024. But even with search and replace, you would still have to read every one of those lines and make sure that that needs to be changed. If, on the other hand, you declare at the top of the program a constant called tax rate, and we do it in all uppercase. We make constants all uppercase so they're easy to recognize as a constant value. Then all you have to do is change it in this one place to 0.024, and then everywhere this identifier shows up, its value is changed. Okay, that's one reason. 2. You know what pi is. Pi is 3.14159. Not everybody does. Suppose that I have distortion coefficient 5.662398. In other words, you're reading a line of code buried in my program, and this number, which we call a magic number, appears. You see this, and you think, well, what is that? I'm multiplying something by 5.66. What is that number? You don't know. But if I identify it, if I write it instead as 5.66, but as distortion coefficient, then you read that and you say, oh, okay, that's distortion coefficient. And I declare that at the top of the program. All you have to do is look up there to see what its value is, and if you need to change it, you can change it. But the point is you have used an identifier that gives meaning to that value. Now, let's take a look at some examples. Now, I want to start with an example that is a bad thing to do. Okay? Here, this programmer has declared a short as a constant, called it 2 and given it a value of 2, and then used it in a computation. When you average two values, you add them and divide by 2. Should that be made a constant? The answer is no. Now, of course, you know what it should be. Av is equal to val1 plus val2 divided by 2. This is how it should appear. Why not make it a constant? Because the way you average two values is to add them, divide by 2, and it will always be that. There is no reason to make this a constant. Furthermore, look at what happens when you reuse that constant. Suppose you want to average 3 values. You add them together and you divide by 2, which you've changed its value to 3. Well, that just looks absolutely silly. Bad idea. If you wanted to set up a constant for that, then call it something that's not directly related to its value. Call it divisor, then set it equal to 2, and then it can be changed to 3 or 5 or whatever. I think the most important thing to keep in mind about these declarations is the use of constants. Constants are extremely important. They make your code versatile, maintainable, modifiable. Remember, of course, that you have to declare every variable before you use it. Use good variable naming convention. Give your variables meaningful names, and make sure, of course, that they compile. Use the most efficient type. If you're going to use small values, then a short is probably good enough. You don't have to use an int or a long. Saves on memory. And that's the end of our session this time.